Be Mazama. I also have to check to make sure we're going to have enough sun down there, because, well, I'll explain that in a moment too. Anyway, part 2 of similarity is that corresponding sides of the figures, of the triangles, are proportional. Oh, I love that word. Corresponding sides of the triangles are in proportion. Oh yes. Oh yes. The reason I wanted to include this section along with grading is because it ties into the idea of grade. It ties directly into the idea of grade. Okay? So let's break down what that means with our example of the 3, 4, 5, and the 6, 8, 10 triangles. Okay, let's make sure we can see those proportions. Let's make sure we can see those proportions. So, is the blue one little? Yeah, the blue one's little. Okay, 5, 3, 4. And you got to realize you can have these triangles stacked any way you pop. I mean, they can be stacked all over the place, right? They can be tilted up on the 3. It could be sitting on the 5. It doesn't have to sit this way, although you usually drive that way, so that's why I'm kind of leaving it the way it is. 6, 8, 10. I'm going to put the dots back in too. I know, it's great stuff.
It's super fun.
Dot, dot, double dot, triple dot, triple dot. Okay. So, what do I mean when I say corresponding sides? What do I mean when I say that?
The same side on both.
Jessica, go with that. The same sides on both. When you say same, nothing's the same in this picture, right? Like if I look at that 5, there's no other 5 anywhere.
Right, the rise.
But right, so, oh, I wasn't thinking of that, but that's very, very good. If we're talking about right triangles, that means the hypotenuse corresponds to the hypotenuse. The rise corresponds to the rise, and the run corresponds to the run. I love that, as long as the pictures look like this. Now that is the caveat. As soon as I tilt this thing like this, then the run becomes the rise, and the rise becomes the run. So there's a more general way of defining it that I like, but I love that as long as the triangles... Did everybody follow what Amber said? Because it works beautifully, so long as the triangles are sitting with the short side in the same place on both, with the middle side in the same place on both, and with the long side in the same place. That works great. The trick is, what if they're not? And we can deal with that, but I love that way. That's too... Josh, go ahead, you had an idea.
I was just going to bring that up. What if the hypotenuse is on the bottom?
Then we got to deal with that, don't we?
We still just look at it as the hypotenuse.
I don't know why I just said that like that. It's all right. Keep going, man. I got to deal with that. Yeah. Damn kids. So this is where those dots come in handy. This is where those dots come in handy. So for example, Jessica, you mentioned the hypotenuse. Let's just talk about this 5 right here. The 5 is between the angle that's 2 dots and the angle that's 3 dots. That means its corresponding side in this triangle has to be the one between 2 dots and 3 dots. That's a foolproof way of corresponding them. Because even if you spun this triangle around, should I draw it spun around so we can see that?
Yeah.
Let's do that, shall we? Green. I'm going to leave this one here, and then I'll spin it like down here. So we'll put I like Josh's, this is going to be too low, I'll put it over here. I'll put the 10 down here, and I'll swing the 8 like up here, and then put the 6 like there. Ish. This is why we have computer graphics. 6, 8. I used to have wooden models when I taught geometry. I'd actually have these things in class, big giant triangles laying on top of each other. But I gave them away when I moved, which is a shame because I'm using them right now. Anyway, this is where those dots come in handy, right? The right angle gets the dot. Between the 10 and the 6, between the 10 and the 6 is 3 dots, which means you've got 2 there. So now it doesn't matter that it's sitting on its hypotenuse. That doesn't matter at all. All you've got to do is look at the dots and see what corresponds. So the one that corresponds to the 5 goes from 2 to 3 dots. And the one that corresponds is the 10, because it goes from 2 to 3 dots. So you would say that 6 corresponds, oh, excuse me, not 6. 5 corresponds to 10. And we should probably, you know what, I got a better idea. Let's do this in color too. And let's do the right colors. So 5 is blue. 10 is green. There we go. And we keep the colors together. Is that okay? Actually, I'll probably erase this. Not that jury, your math wasn't awesome. But it's, sorry. Give me another set that corresponds.
6 is green.
Ashley, go ahead. So 3 corresponds to 6, yes? If I go in the same order, it's okay. Give me the last one. 4
And 8.
correspond. Tell me your name.
Jessica?
Jessica, thank you. Wait a minute. Okay, good. 4. You just don't see my robot mind working. Okay. 4 corresponds to 8. Yes, I know, it's thrilling. So now, mathematically, what's cool about all those correspondences?
They're half.
If you look along, good, because they're similar, they're corresponding, and because they're corresponding, they're similar. It's kind of an A, B, B, A. If you look at any of the numbers in blue, they're half of their corresponding numbers in green. Conversely, number in green is double its corresponding number in blue. 5 is half of 10, 3 is half of 6, 4 is half of 8. That's beautiful. Those are called scale factors. Scale factors. That's actually the scale factor. You guys have used these, but you probably haven't used them with geometry. You've probably used them on a map. For those of you that still use maps. Now, I had a rude awakening. I went to see one of my favorite bands play in Seattle about 6 months ago. And I went to see him after they played, and he was sitting at the bar. One of the guys sitting at the bar, my friend Josh, and he was loaded. And he was talking, he was like, "Merle, you used to be in a band." I'm like, "Yeah, I used to be in a band, Josh." And he's like, "Yeah, you had to use maps and stuff back then, right?" And it was just so adorable. Like, you don't use maps. It's like, what's a map? I mean, he was completely lit. It was adorable to watch. But I began to realize that, how many of you still use maps on car trips? A few of you do. How many of you just use your phones? Yeah, that's the change of it now, is you hit go. I went to Portland to find a show on Saturday night. We were playing a show up at the Tonic Lounge on Sandy Boulevard. And the freaking thing shut down about a half mile. I'm like, what am I going to do? I'm like, wait a minute, I'm an old man, I got a map out. But I begin to realize that art is getting lost. And how is this related to maps?
It's directly related.
How?
Yeah.
Because a map has a scale on it. 1 inch equals a mile, for example. 1 inch equals a mile. Which means if you trace out your path on a map, and it's 18 inches, that's going to be 18 miles. And it gets interesting when 1 inch is something like 50 miles or something like that, or a half an inch is this. But that's what this is. It sets up the ratio, the scale set on the map equals a proportion when you apply it. That's what we're getting to with similar triangles. Go ahead, Josh.
So the ratio for these two triangles would be 1 to 2.
Mm-hmm. 1 to 2 or 2 to 1. Doesn't matter to me which way you look at it. Yeah, it doesn't matter to me at all which way you look at it because it's your choice on how to set the equations up. Yeah, so the ratio, the scale factor for these triangles is 1 to 2. Or 2 to 1, depending on which one you're referring to first. Does everybody buy that?
So would you replace the words corresponds to with a colon? And
You totally could. You totally could, although I like to say that it's okay, Jessica, when we actually start using these to solve problems, then we can set up the colon, double colon, equal signs, all that fun stuff, fraction bars. Yeah. Did you notice anything else? What's 3 divided by 4?
75.
0.75?
1.7.
6 divided by 8. 5 divided by 3. Oh, I'm such a bastard. 5 divided by 3.
11.
You work for the government, don't you? That's how we can afford everything, because of that math. 5 divided by 3. 1.6666 repeating. 10 divided by 6. 1.66666. I find it hard to say that number without doing like this. Yes. So 5 divided by 3, 1.67. 10 divided by 6, 1.67. 8 divided by 10, let's go easy.
8,
8 divided by 10,
20.
80%, 0.8.
No, no,
4 divided by 5.
0.8.
80%, 0.8. You see? So those aren't scale factors. Because notice how they were all different? Every one of those, but if you pair them off in the same way on both triangles, the fraction is the same. That doesn't carry a name like scale factor or a percentage, whatever, blah, blah, blah. But it's still true. That's the beauty of these similar triangles, because you can actually set them up to use them and do stuff. So let me paint the picture of what we'll do on Monday down at Mazamas Field. And I have to check at 8 o'clock in the morning to make sure I have enough sun to do this with. Okay. I know we can do one thing without sun. The second thing might be tricky. I'll have to work on it. But
Wait.
go ahead, Josh.
So on these triangles, going back to
Yeah.
so wouldn't the angle adjacent to 5 and 4, like the one that both triangles share right
Yes.
there, wouldn't that be a 75-degree angle?
No, it's a 75% grade,
Oh,
which corresponds to the angle from that chart. I use my calculator to do it. It ends up being about 37 degrees.
okay.
But that's where that chart would come in handy for you to look up,
Got it.
right? That's where you have to go to the chart and get the reference. The thing about it is, for small grades, back to Christie's small grades, roughly the angle is ish half the grade. Ish. So if it's a 6% grade, it's just about a 3-degree angle. If it's an 8% grade, it's ish a 4-degree angle. If it's 2% grade, it's a 1-degree angle. That gets blown out of the water real quickly once the angles start getting big.
Okay, so would another way to find the angle
Uh-huh.
be dividing 90 by, oh goodness, never mind.
No, wouldn't that be nice?
Yeah. never
Yeah, this, what Josh, yeah, wouldn't that be nice?
mind.
What Josh is, no, I love what you're doing, and what you're doing is perfectly logical. See, okay, thank you for bringing this up. It's actually a neat little connection to what we've been doing for the past 2 days. Grade, similar triangles, and linear modeling, all of which we're going to be doing in the next couple of days together. We've done grade, we're still kind of talking about it. We're in the middle of doing the similar triangle stuff, and we're about to start in the world of linear modeling. All of that stuff does linear change in data. If X changes this much, Y will change this much. And no matter how much X changes, Y changes proportionally. So if the scale is 1 to 2, if the first one changes 3, the next one has to change 6. If the first one changes 5, the next one has to change. If the first one changes -4, it has to go -8, right? Multiply by 2. Just you multiply by that. Sorry, that's a bastard move. I'm sorry. That wasn't fair. That wasn't fair. It was way too early for that kind of stuff. That's linear. The problem is when you assume everything is linear. And the thing about tangents are, they're trigonometric. The curve, so you guys know what a linear function looks like. You know what a linear graph looks like. You've been dealing with them since you were teeny tiny, right? So you've got, they look like this, actually. You don't have to draw anything. They look like this. You can slap axes on this if you want to. There, they look like that. It's linear. Tangent curves are one of the more beautiful curves. They look like this. What color? Purple. They look like this. They're not linear. Now, what I'd like to do in this class, with your permission, is to tame these curves that do this by hyper-focusing on tiny sections of them. Because if you can hyper-focus on tiny sections of them, they look like straight lines. For example, if you took a microscope, even if this was drawn well, and I didn't draw it very well, I drew it with a big fat marker very quickly. This is very curvy, yes? It's very curvy. If you picked a point on this and a point on this and connected them with a line, that's not very close to the curve at all. It doesn't look very close to the curve, not even a little bit. Exactly, no. But if you start moving these points closer to each other, you begin to trace more and more of the original curve with that line that hits it. And if you can shrink those points together very, very close, that little tiny section of curve begins to look like that line you just drew. And then you're like, we like that. Because we like lines. We don't like this trigonometric crap you talked about 5 minutes ago. As a matter of fact, Sean, when you mentioned the word trigonometric, I stopped listening. But if you can zoom in, you then have an understanding of what your speedometer is telling you in your car, which is pretty badass. Please tell me your name.
Marichelle.
Marichelle, go ahead.
Does this correspond to like when we were doing the grade of the stairs and how you measure the individual stairs?
It will. We are going to grade curves, not just stairs. Imagine if the stairs were shaped like this.
Right.
We can now do what's called an instantaneous or a point grade on a section of the stairs.
But you don't have to do all of them.
You can't because it changes too much, right? That's the point is these curves are constantly in flux, where a line never is in flux. Linear thinking is great until the data becomes nonlinear, right? As soon as your data is nonlinear, it's like, well, I can make it be a line. Well, that's good. You're going to be wrong all the time. Except for those places where the line approximates what the curve is doing. Think about it this way. You throw a rock up in the air. What happens? It goes up and it comes down. What happens right before it starts coming back down again? It hangs there for a split second while it changes direction. You can, at the apex, exactly. You can say that at that moment the rock isn't going anywhere. It's not changing its distance at all. So at that very moment, you can represent its speed as a horizontal line. Zero. Zero slope, zero grade, its speed would be a horizontal line. All you're doing with curves is piecing those lines together to make the curve. And that's what we're going to do with my bike, going down the hill, is put these, they're called secant lines and tangent curves. It's super fun. But that's how your speedometer works on your car. I mean, when it says you're going 40 miles an hour, when are you going 40 miles an hour? Right then, at that moment. You might average 20 miles an hour for the whole trip. But at that moment, you're going 40, and at that moment, you're going 65, and at that moment, you're getting a ticket for going too fast through warm springs. Go ahead, John. Talking to my wife.
So how, we probably went over this already, but how would you find the angles for these?
It's just a tangent table.
Oh, just a tangent.
That's the only way right now, without teaching you guys the algebra behind the tangent function, which I would do to my worst enemy. Use the tangent table, look it up. And if you want more, on the extra resources page for grade, there's a TI set of button pushes you can do to do what I just did up here. It's called the arctangent function, yeah. Just make sure you follow the instructions. You have to set your calculator in the right mode and blah, 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 blah. It seems like a bunch of hooey, but I mean, it's trigonometry.
Okay.
Which is often confused with hooey in certain cultures. Cool? Yes?
So are the curves like the curves of a road then? When you put these like
They're more predictable, but yeah. These are governed by algebra. And trigonometry, really, but they're governed by algebra. What you're doing is what would be on the horizontal axis is the angle formed with the two pieces. And what you're actually graphing with this is the tangent, is the grade. So what you're really looking at in this picture is a picture of the angle formed and the grade formed by that angle. So you can see how the grade is beginning to shoot up towards infinity. Did you notice that on the grade table, the tangent table that we looked at? Once the angles get pretty big, the grades get really big. 75%, they go over 100% very quickly. Remember what angle had 100% grade? Do you remember it was 45 degrees,
yeah.
was 100%? 200% sounds like a lot, but it's only like 62 degrees or something like that. 300% is something like, I think it's like 81 or something. You can't have, it goes well over 100, but there's no grade at 90 degrees. At 90 degrees, you lose your run. Your run vanishes, and it's all rise. So you've got rise divided by 0, which is undefined. But that's why this thing goes shooting off to infinity. Because it is, it's shooting off to its infinity. If you got 89 degrees, 89.9, 89.99, 89.999, those grades are ridiculously large. Because your run is shrinking and shrinking and shrinking and shrinking, and your rise is growing and growing and growing and growing. And it doesn't take much of a change in angle to get a whole hell of a lot of change in vertical. So, it kind of makes sense. It's kind of trippy, it's kind of heady, but at the same time, it's freaking cool. Because it explains that table to you an awful lot. At small values of the angle, like right here, that curve, and I didn't draw it very well, it's pretty flat right there. It's pretty flat, and then it creeps up, and then it really does that. It's not linear. That's the big takeaway is it's not a line. It's very much curving.
like
and then
roads aren't?
Yeah, but roads they're kind of random. This is very predictable.
Oh.
It's mathematically predictable versus a road, which is kind of like, well, there's a mountain, make it go around it.
Yeah.
You know?
Okay.
How do you decide that? How do you decide when to go around a mountain and when to just go through it?
Yeah.
Money?
Money.
Is that what it is? Can we afford to blow through the mountain this year?
It is actually.
Really?
And it's like they look at the structure of the mountain, the size
decide whether it is structurally sound to go through the mound or just.
That makes a lot of sense.
That makes sense.
That makes a lot of sense to me.
Geologists decide.
Thank God, and it's not just the business people. Thank God. Please.
When you increase your grade
Yes.
to a point where your run and your rise,
I'm gonna fire this thing up. You guys got some great questions. I'm gonna fire the projector up to get some more better graphs on the board. Go ahead. Go ahead.
when you increase your grade enough
Yes.
where your rise and your run
Mhm.
won't ever create a triangle, in a sense, does your grade just equal infinity?
That's a damn good question. I'm gonna answer it mathematically. No. Now, next. Because you can't equal infinity. Infinity isn't a number, it's a direction you're heading towards. The symbol for infinity, which I know the car now uses, which I love. The symbol for infinity implies a direction you're heading towards. When you see a positive infinity sign, it means it's getting larger without bound. It's never slowing down, it's never stopping. It might alter its path on the way there, but it's not ever going to turn around and come back again. So, when you said, I love how you said, when you get to where you can't make a triangle anymore, you can never get there. Or you can get there, I guess. But then you don't have, the grade doesn't exist at that point.
Yeah.
There is no grade. Think about it this way. When you guys were in Math 60 or Algebra 1, what's the slope of a horizontal line? Horizontal.
Zero.
It's 0. Why?
Because that's what the arrow.
Because that's what they told you. Let's go with a better answer. What is slope?
Rise over, or rise
It's rise over run. It's the same as grade. So on a horizontal line, what's the rise?
zero.
0. What's the run?
Zero.
Careful. It's something. A horizontal line does run, doesn't it? It runs a certain distance. If the run was 0, it would be a point. No rise, no run, it would be a point sitting on the plane. So a horizontal line does have some kind of run. So you got 0 divided by something. That's 0. How about a vertical line?
Undefined.
You were taught to say it has an undefined slope.
Yeah.
And I love that you were taught to say that it has an undefined slope because it's got a lot of rise, but 0 run, right? But 0 run. And because it has 0 run, you're dividing by 0. Now, the mathematical answer of no means you can't do like 8 divided by 0 equals infinity. So what infinity becomes, and let me log this in and get a better tangent curve for you guys. You guys are asking, I wasn't expecting the discussion to go this way. If it's okay, I want to keep it going to answer the question fully. It'll lead right back to the similar triangles because it's all part of it, and it's part of Josh's question about the tangent and why it's so hard to calculate. But you can't say it equals infinity.